Is a way of finding the derivative for certain types of functions. Now, it is related to the work you've done with the definition of the derivative. Maybe you've picked up on a pattern already. We'll have to see. So, remember, the derivative tells you, the definition of the derivative allows you to write an equation that tells you the slope of the graph at any point on the graph. Looking at some examples of certain types of equations will hopefully help you see what the power rule is and how it can be used. So what I want to do is take a look at some very specific examples, and they are as follows. So what we're going to first look at is I'm going to look at f of x. So let's bring this up. F of x equals 2. G of x equals 4x, h of x equals, let's go with 3x squared, and last but not least is going to be, you guessed it, j, because no one actually uses I. Looks like a 1. J of x equal to 6x cubed. Now, pattern-wise, remember, f prime is the derivative of f of x, and it would represent the slope at any given point. 2, f of x equals 2, is a constant, aka horizontal line, which has a slope of 0. We knew that. G of x. Well, g of x is linear, and we know it goes like that because it has a positive slope of 4. Is the slope 4 the whole time? Yes. So that means that g prime of x has got to be 4. That is what you're going to get as the slope at any point, no matter what x you put in. Now, looking at this, if you have something that's a constant, then that seems to have a slope of 0, no contribution. Slope of 4. What did you notice when you were finding the derivative of these other functions? I don't know if you noticed, but we gave you examples of, well, quadratics mostly, right? So h prime of x, if you work that out, and I'm not going to run through the process, works out to be 6x. Now, let's take a giant step back here. I would argue the following, that this 2 is really the same as 2x to the 0. What do you think? And this 4x is really 4x to the first. So are all these functions really related? Yes, they're all power models. So those something where you have these are all called power models. The reason is we have x being raised to the and some sort of constant exponent. Now it could be positive, it could be negative. In this case I've chosen 0, 1, 2, 3. Well, you'll see why in a second. How is this related to this? Well, if you look here, well, let's come back to that. Maybe there's a pattern, but so here x becomes just, there's no x there anymore. Is that the same as saying x to the 0? Think about that. Now, does that fit? Watch this. 2 becomes 1. So I would argue that if we were going to look at j prime of x, which, yes, that's what we're going to do, j prime of x, that it's going to become something x squared. So if I'm looking at this, and we'll come back to you in just a sec. 1 becomes x to the 0, which is a fancy way of saying 1, right? It's just 4, really. Squared becomes first power. Argument, cube becomes second power. Okay, 2 became 0. How? We'll back up for a second. 4 became 4. How? It didn't change. I would argue we multiply by 1. We'll see why in just a second. Because if we look at this part right here, to go from 3 to 6, well, we could add 3, or could we multiply by 2? Multiply by 2. 2 times 3 is 6, and then the power drops. Pattern. 1 times 4 is 4, and then the power drops. X to the 0 we don't normally write, so we just say 4. What is 0 times 2? 0. X to the, it doesn't matter because it's 0. So the argument here is that we take this 3, we multiply it by the 6, we get 18, and then we go ahead and boldly bring the power down 1, so it would be 18x squared. That, my friends, is the power rule. So, to sum up, for any given function, a times x to the n, to find the derivative of that function, you take and multiply by the exponent, and then multiply that by a coefficient of it's there, right? And then x does what? Well, the power of x drops 1. Now, is it possible to have a function that is ax to the n plus bx to the, bx to the, let's get this right here, bx to the n minus 1. Let's call that r of x, right? If I wanted to find the derivative, what could I do? Well, it turns out that this is a composition of two functions being added. So could we say that r of x is really a of x plus b of x? And then the argument is if I find the derivative of one and find the derivative of the other and then add them, shouldn't that work? Well, this has a certain slope, right? This has a certain slope. So this slope at any given point is going to be a number plus whatever that is, right? So the argument is if I want to find r prime of x, all I need to do is find the derivative of the a of x and the derivative of b of x. More simply put, we'd say that r prime of x would be, well, we take n and multiply it by the a, so n times a. This looks exactly like the power rule, right? Then drop the power 1, n minus 1. Plus, well, now we take the n minus 1, which is just a power, right? Just one lower than the n, right? We wrote this in standard form. Times b times x, but now it becomes n minus 2 because the power dropped. N minus 1 became n minus 2. Let's take a look at some examples. So, find the derivative of the following functions. Here it goes. Don't blink too many times would be my advice. G prime of x equals 2 times 3, or 6, x to the first, but we don't write it, plus, that is linear, or you could think of it as x to the first. 1 times 2 is 2. This drops to x to the 0th, which is 1. What is the derivative of negative 1? It's not. It's constant, no effect. That is what g prime of x is. You're done. H of x is going to be rewritten slightly differently. Now, is something raised to a negative exponent still a power model? Well, yeah, x is still being raised to some constant. So pattern-wise, what have we got? Well, we know that the derivative, h prime of x, is going to, well, the 7 is going to become 0. This minus x squared, that's a negative 1 times x squared, is going to be minus 2x. What about this? Well, negative 1 times 3, that's easy. It's negative 3 x to the, well, what's negative 1 minus 1? Negative 2. So I'm going to simplify this slightly. Negative 3. What does a negative exponent do? What does an negative exponent do? It takes the reciprocal. So this becomes negative 3 over x squared minus 2x. And, well, that's it, because we don't normally write plus 0 unless we feel like wasting a lot of time, right? One last one. Notice this term. This is the same as saying 7 minus 2x, easy, easy, minus 4x to the, well, it's in the denominator because we're dividing, negative 3, right? So, here we go. Q prime of x. The derivative of any constant, 7, a number, is 0, goes away. That negative is part of the 2, so that's negative 2 times x. What is the slope? Negative 2. Think of it like that's a linear graph. That's a linear term. Its slope is negative 2. Or 1 times negative 2, and then we drop that. Negative 3 times negative 4 is positive 12. Yes, you guessed it. X to the, what is negative 3? Take away 1, negative 4. Under normal circumstances, we'd write that as, well, I'm going to put the variable first. That'd be preferentially what we're looking at. 12 over x to the 4th minus 2, though this is also correct. And that's it.